Good morning and welcome to today's class. Last class we have found some basics in function analysis mainly from the linear algebra. Now here we will have quotient spaces. For a subspace E1 of E, we define the quotient space of E with respect to E1 as E by E1, where E by E1 is defined as set of all equivalence classes X, you can say set of all X such that X belongs to E. Here one X means it is of the form X plus E1 called the cosets of A. Cosets of E. So as this bracket X means it is going to be the coset of E. So E by E1 means the collection of those cosets of elements of E. So two cosets X and Y are either disjoint or coincides. So if there exists an element in the intersection means then Z belongs to your coset X and Z belongs to coset Y. Now if Z belongs to coset X means Z is equal to some X plus P where this P belongs to E1 and therefore X minus X is equal to P which belongs to E1. We will get Z minus X that's equal to P that belongs to E1. Similarly Z minus Y also belongs to E1. Therefore, Z minus X minus Z minus Y also belongs to E1, which implies Y minus X belongs to E1. Now consider A belongs to your coset X. Then if A minus X belongs to E1, which implies A minus X belongs to E1. Now A minus Y can be written as A minus X minus Y minus X. This is again belongs to E1, which implies A belongs to Y plus E1, which implies A belongs to the cosets of Y. Therefore, coset of X is contained in coset Y. Similarly, we can prove the other way inclusion. So, either two cosets should be identical or disjoint. Now we are defining a linear structure on E by E1 by the coset addition, that is x coset of x plus coset of y is equal to coset of x plus y, and a into coset of x is equal to coset of ax. Now as a remark, the coset of 0 is the 0 vector of the new space E by E1. Coset 0 is the 0 vector of the new space E by E1. The dimension of E by E1, or we'll say the quotient group. We have defined that in that way. Is the quotient space. Yeah, quotient space we have defined. So we will call this as a quotient space. So the dimension of this quotient space E by E1 is called the codimension of E1. It's called the codimension of E1 with respect to E, and we denote it as codimension of E1 with respect to E, or we will say that dimension of E by E1 or codimension of E1 if E is very evident. Some examples. Consider C and C0. C means set of all convergent sequences and C0 means set of all sequences which converges to 0. Now suppose we are taking C by C0. So C by C0. Now X belongs to C, then X is of the form some Xn 1 to infinity form. Now X plus C0 that's equal to A into 1 plus C0. I repeat, now x plus c0. X plus c0 means it's a coset. So it belongs to a coset. Coset determined by x. Okay. Now x plus c0 is equal to A into 1 plus C naught, where A means limit of the sequence xn and 1 is the constant sequence with all its terms equal to 1, and 1 is a constant sequence with all its terms equal to 1. Thus, the coset of x can be written as set of all x plus c naught such that x belongs to c, and that can be written as a into coset of 1. That means codimension of c naught by c or codimension of c naught is 1. Now next definition, the vectors x1, x2, etc., xn are said to be linearly independent related to the subspace E1 subspace of E if from sigma I equal to 1 to n ai xi belongs to E1, it follows that a1, a2, etc., an equal to 0. So up to now we have studied the linear independence of vectors in a vector space. Now we are studying the linear independence of these vectors related to a subspace. That means if you're having sigma I is equal to 1 to n ai xi is in E1, then a1, a2, etc. an equal to 0 means we will say that these vectors x1, x2, etc. xn are linearly independent related to a subspace E1. Now lemma 1.1.4, the dimension of E by E1 is n if and only if there exist x1, x2, etc., xn linearly independent vectors. So the dimension of E by E1 is n if and only if there exist x1, x2, etc., xn linearly independent vectors related to E1 such that for every x belongs to E, there exists a unique set of numbers a1, a2, etc., an and a unique vector y in E1 such that x can be written as sigma I is equal to 1 to n ai xi. That is nothing but the linear combination of vectors xi plus some y. Moreover, the cosets x1, x2, etc., xn be a basis of E by E1. Now its proof. What we want to prove is that first of all, x can be written in this fashion and this will form a basis of your E by E1. So proof. First we consider this as a basis of E by E1. Then the vectors xi for I is equal to 1 to n are linearly independent relative to E1. Because if you are writing sigma I equal to 1 to n ai xi belongs to E1, then sigma ai into, since this is going to be the basis, we are writing an element as a linear combination of the cosets. So this can be written as sigma I equal to 1 to n ai xi coset, and that is nothing but 0, and hence why we are having this to be 0, because in a quotient space we know that even e by even when you are considering even is going to be the 0 over there, and hence a1, a2, etc. all are equal to 0. Since this is 0, we are having this belongs to E1. So in E1, if means you will get a1, a2, etc. all are going to be zeros. Now for every coset x, we have left the coset of x is equal to sigma I equal to 1 to n ai into xi. That means this is the basis element. So this can be written in this way, and now the we have the coset of x is equal to coset of sigma I equal to 1 to n ai xi, and in set notation it can be written as sigma I equal to 1 to n ai xi plus yi for yi belongs to E1. Therefore, x can be written as sigma I equal to 1 to n ai xi plus some y for some y belongs to E1. Now we want to show that such a representation is unique. We have expressed x in our desired form. Now we will prove that such an expression is unique. If suppose X can be written as sigma I equal to 1 to n bi xi plus some set for some set belongs to E1. Then we can subtract these two. So you get 0 is equal to sigma I equal to 1 to n ai minus bi into xi plus y minus z. That is sigma I equal to 1 to n ai minus bi into xi is equal to z minus y. Z belongs to E1, y belongs to E1. E1 is a subspace, therefore we will say that this belongs to E1. So sigma I equal to 1 to n ai minus bi into xi belongs to E1. That implies ai minus bi is equal to 0 and z minus y is equal to 0, which implies a is equal to bi and z equal to y. Such a representation is unique. Now conversely assume that for each x belongs to x can be written as some sigma I equal to 1 to n ai xi plus some yi. Now this hold for x1, x2, etc. xn linearly independent relative to E1. The cosets x1, x2, etc. xn are linearly independent since if we are taking the summation I equal to 1 to n ai, uh, the coset of xi means it can be written as the coset of sigma I equal to 1 to n ai xi, and this equal to 0 coset. Then sigma I equal to 1 to n ai xi belongs to E1. Now this belongs to E1, hence A1, A2, etc. An equal to 0. And let x be an arbitrary coset, then x minus sigma I equal to 1 to n ai xi belongs to E1. Therefore, the coset of x is equal to sigma I equal to 1 to n ai xi, and that can be written as sigma I equal to 1 to n ai into coset xi. Therefore, the cosets x1, x2, etc. xn form a basis of E by E1. So we have proved that the dimension of E by E1 is n if there exists a x1, x2, x3, xn linearly independent vectors related to E1 such that for every x belongs to E, there exists a unique set of numbers a1, a2, etc., an and a unique vector y in E1 such that x is equal to sigma I equal to 1 to n ai xi plus y. Moreover, we have proved that the cosets x1, x2, etc. xn is a basis of E by E1. Okay, now we will move to normed spaces. We have studied in linear algebra what's the norm in terms of your inner products. I'm sorry, not in inner products. We have studied normed spaces. So a norm x for x belongs to E is a function from E to R satisfying the following properties. This property we have already studied. That is, first one is positivity. That means norm of x should be always greater than or equal to 0, and if norm of x is equal to 0, even only if x is equal to 0. And second one, norm of lambda x is equal to mod lambda into norm x, and norm of x plus y is less than or equal to norm of x plus norm of y. This is called the triangle inequality. For this is valid for all x comma y in E. and for all lambda in your scalar field. Now with this norm, we define distance between 2 points x and y. That is dxy we will define as norm of x minus y. Now by the triangle inequality we will get norm of x minus y can be written as norm of x minus z plus z minus y. Now we can split the norm by using triangle inequality. We will get this is nothing but d of xy. So d of xy is less than or equal to d of xz plus d of zy. Therefore, d of xy is less than or equal to d of xz plus d of zy. Now we will use the notation as x for the normed space. That means SA together with a norm. We will say this is a normed space. Now hereafter when we are say writing X means its meaning is that it is a normed space. So X is equal to E comma the norm. Now definition 1.2.2, that means the comparability of norm. The norm, one norm, is said to be stronger than two norm if there exists constant c greater than 0 such that norm 2 is with respect to a norm of x with respect to the second norm is less than or equal to c into norm of x with respect to the first norm for all x belongs to E. That is two norm, we are taking norm 1 and norm 2, and we say that the first norm is stronger than the second norm, means the second norm with norm of an element with respect to the second norm should be less than or equal to some constant times some norm of first x, where the constant should be greater than 0. Now the norm, this norm, one norm and two norm are said to be equivalent if there exists a constant small c and capital C both greater than 0 such that c into norm of x with respect to the two norm should be less than or equal to norm of x with respect to the first norm, which is less than or equal to capital C into norm of x with respect to the two norm for all x belongs to E. So with this I'm stopping today's class, and next class we can discuss some more detail about functional analysis. Okay, thank you.